You know, we use huge online services every single day without even thinking about it. But what's really going on behind the curtain? Well, it's basically a bunch of computers that all have to agree and work together, perfectly, all the time. So in this explainer, we're going to pull back that curtain and really dig into the brilliant ideas that let these systems coordinate and give us the rock-solid services we can't live without.
So, let's kick things off with the big question. Why is it that your favorite app just keeps working, even when one of its servers inevitably fails? I mean, a server can go down for a million reasons, right? A power outage, a weird software bug, you name it. The secret sauce, the real magic here, is some seriously clever engineering. It's all about building one single system that is way, way more reliable than any of its individual, frankly, pretty unreliable parts. Okay, to really get how that works, let's start with the simpler but super common problem that engineers face all the time. It's called the noisy neighbor problem. And it's what happens when you get totally different kinds of jobs all stuck in the same line, and it just causes complete chaos for everyone involved.
I think we can all relate to this. Imagine you need a password reset email, like right now. It's a tiny, urgent task that should take literally milliseconds, but it's stuck. It's trapped in a queue behind some gigantic, resource-hogging job, like crunching a massive monthly analytics report. And what's the result? Well, your customer's locked out, they're getting frustrated, and your entire system just feels slow and clogged up. Not good. Now, the solution here seems pretty straightforward, right? It's called workload isolation. You just create separate lines or queues. All the quick, zippy little tasks go into one queue, and all the slow, heavy-lifting jobs go into another. Then you give each queue its own set of dedicated workers. Boom! The noisy neighbor is off in its own corner and can't slow anyone else down. Problem solved. Or is it? Well, kinda. See, by solving that one problem, we've accidentally created a brand new one. And this one is way bigger. We now have this single central coordinator that's in charge of routing all the tasks. So what happens if that one thing, that central brain, goes down? The whole system, every single queue, fast and slow, just grinds to a complete stop.
And trust me, these failures are not some hypothetical what-if scenario. They happen all the time. I love this quote from engineer Coda Hale because it just perfectly captures how messy and unpredictable the real world is. We're talking everything from simple hardware failures to, a pickup truck literally smashing into a data center's air conditioning system. The key takeaway here is that partial failures aren't the exception. They are an absolute 100% certainty you have to design around. So how on earth do you design for that level of chaos? You do it with a really foundational pattern in computer science called leader and followers. This is the secret to how distributed systems manage to bring order to a world where, let's be honest, any piece of the puzzle can just vanish at any moment. And the idea is just so elegant. Instead of having one single special controller, which we already saw as a huge risk, you have a whole group of servers. And through this cool democratic process, an election, one of them gets chosen to be the leader. This leader is now the one and only source of truth. It makes all the calls. The rest of the servers, they become followers, and their only job is to just perfectly copy everything the leader does, creating exact replicas of its state. This visual shows the flow perfectly. So Neptune here is our leader. See how all the requests from clients go straight to it? That establishes it as the single source of truth. The followers, Jupiter and Saturn, their job is simple. They just replicate what Neptune decides. This is absolutely critical because it prevents any conflicting updates and makes sure that every single part of the system sees the exact same, perfectly consistent version of reality. Okay, but how do the followers actually know the leader is still alive and kicking? Well, it's through these constant, tiny little messages called heartbeats. The leader is always sending them out, every few moments just saying, "Hey, I'm still here. I'm still in charge." And as long as the followers keep getting those heartbeats, they know all is well and they just keep on following. But the second those heartbeats stop, well, that's when everything changes.
This right here is the moment of truth. This is recovery in action. The leader is gone. For all intents and purposes, it's presumed dead. Now, the system has to heal itself. It has to automatically and, more importantly, safely choose a new leader, all without a human having to lift a finger.
So how does this election work? It basically happens in 3 steps. First, one of the followers realizes, hey, I haven't heard a heartbeat in a while, and its internal timer goes off. That follower then switches roles and becomes a candidate. It immediately starts asking all the other servers for their vote, and if
And this is a big if. It can get votes from a majority of the servers, what's known as a quorum, then it wins. It gets promoted and becomes the new leader.
And right here you can see that whole democratic process playing out. Look, Peer 1 has become a candidate, and it's sending out vote requests to its buddies. Now, after checking a couple of important rules, Peer 2 and Peer 3 both say, "Yep, you've got my vote." And just like that, with a majority in hand, Peer 1 has the green light to take over as the new leader.
But hang on, there's a super important safety rule here. A server can only win an election if it has the most up-to-date log of information. This is the critical guarantee. This is how we make sure that no committed data ever gets lost in the transition. The new leader has to be able to pick up exactly where the old one left off without missing a single beat.
All right, now we've got to talk about the most dangerous failure mode of them all. This is the stuff of nightmares for distributed systems engineers. What if the old leader wasn't actually dead? What if it was just isolated, temporarily cut off from the rest of the network? This situation can lead to an absolutely catastrophic scenario.
This condition is called a split brain, and it's as bad as it sounds. The system literally splits into two independent factions. In one corner, you have the old leader, totally oblivious, still alive and thinking it's the boss. In the other corner, you have the rest of the followers who have just held an election and picked a new leader. So now you've got two leaders, both actively taking requests, both making decisions. The system's view of reality is splitting apart, and your data is getting corrupted. It's a disaster.
And yeah, this really drives home just how bad that conflict is. You have two different nodes, and each one is living in its own separate reality. The old leader is over here accepting rights from one group of clients, while the new leader is over there accepting rights from another group. There is no single source of truth anymore. And that leads to irreversible data loss. You can't just glue it back together.
So how do we prevent this absolute nightmare? Thankfully, there's a beautifully simple and incredibly powerful solution. It's called a generation clock. You can also hear it called an epoch or a term. The easiest way to think about it is like a version number for a leader's term in office. And the rule is simple. Every single time a new election starts, that number goes up by 1.
So, for example, let's say our old, isolated leader was happily chugging along in Generation 2. It's still running, it thinks everything is fine, but his term is now totally outdated. It's completely unaware that a new election has even taken place.
Meanwhile, the newly elected leader kicks off its term in Generation 3. So now, what happens when that old leader finally reconnects and tries to send commands? The other servers will immediately see its old, outdated generation number. They'll see 2 when they know the world is on 3, and they'll just flat out reject its commands. The rule is simple, it's absolute. The leader with the higher generation number always wins. And just like that, split brain is completely averted.
Okay, let's zoom out and pull all these pieces together. When you combine these powerful patterns, you've got leader election, you've got majority voting with quorums, and you've got these generation clocks to prevent split brain, you can actually build one single, incredibly resilient system from a whole bunch of parts that you know are going to fail.
And look, this isn't just some abstract academic theory. These ideas are the absolute bedrock of the most critical, mission-critical infrastructure that powers the internet today. I mean, just look at this list. Systems like Apache Kafka, which is used for enormous event streams, etcd, which is literally the brain of Kubernetes, they all rely on these exact same fundamental principles to stay online.
You know, designing one of these systems is a lot like trying to navigate a ship through a really treacherous sea. There are just unpredictable storms everywhere, and countless ways for things to go horribly wrong. But these patterns we've talked about, these algorithms for getting everyone to agree, they're like the reliable maps and the trustworthy compasses that let engineers chart a safe course through all that chaos.
And that brings us full circle, right back to where we started. That seamless, it just works reliability that we all take for granted every day, it's not magic, not at all. It's the result of some truly brilliant engineering, all designed to solve one fundamental problem. How do you get a group of unreliable computers to agree and build a single, reliable, fault-tolerant system that's stronger than any of its individual parts?